In this video, we're going to discuss conservation of momentum. Conservation of momentum is pretty much why we use momentum in physics. When you think about different physics quantities, you can really multiply any variables together and call it something. But the reason we multiply mass and velocity together to get momentum is because momentum is significant, and the main use is when it's conserved. And so let's talk about what that means. So, conservation of momentum basically means the momentum's not changing in the system. So our momentum initial equals our momentum final. Or you might see the change in momentum equal to zero. And that's that total momentum of the system. So if we have multiple objects in the system, then their net momentum is going to be different. So if we have this initial momentum equals the final, we could also write it out as the initial, like the separate masses, the separate mass times velocity initials, right, equal the final of each one added up together. But it doesn't mean that each object's momentum is going to be exactly the same. It just means when you add them, they equal each other. So let's talk about when can we actually use the conservation momentum. So let's say we have like the ground, and I'm going to make the ground a little bit lower. Let's say we have the ground and some ball, right? And the ball is falling downwards, the velocity. In this case, if we take the system to be the ball, we cannot use conservation momentum because there's a net force acting on this ball, and it's the force due to gravity. But if we have this same exact situation with a ball falling down to the ground, but now we take our system as the ball plus earth system, like that, then this force due to gravity is within the system, and there's no net force, so then momentum of the system is going to be conserved. And so we'll see how this can be used, and the main thing that you'll see momentum being used for will be collisions and explosions. So if you have two boxes moving at each other and they collide and they bounce off or they stick together, you can use conservation momentum. Whereas energy deals a lot with changing in heights with speeds, momentum does a lot with interactions between objects. And when you have them in the same system, their total momentum is conserved. That's why we use this. So let's look at an example of this conservation of momentum. So we have a block of mass m slides at the constant velocity of 15 meters per second. The box then explodes into two pieces. One piece has 1/4 the mass and slides at 20 meters per second in the same direction as the initial block. What is the velocity of the other piece? Okay, so let's draw what we have, right? We have a box right here, and it's moving with some velocity initial, and that'll be 15 meters per second. And so when it's sliding, it then breaks off into two pieces. And so one piece moves in the same direction as v final 1, we'll just call it, and this has 1/4 the mass. And so the other piece must have 3/4 the mass. But we don't know what this velocity is. The velocity final 2 is what we want to figure out. But we know what the initial system was. So the system is going to be the block in this case. And since it's sliding at a constant velocity, we can assume there's no frictional forces, because otherwise it would be slowing down, or you would have to also have an applied force. But since it's moving at a constant velocity, there's no net force. So that's why we know we can use conservation of momentum in this situation. Okay, so let's write out our variables so we have them. So the mass initial is just m, because before it breaks, it's just going to have a mass of m. That's what it says right here, mass of m. And then we have an initial velocity is 15 meters per second. Then we have our m1 final, which equals 1/4 the m. We have our m2 final, which is 3/4 m, because it's just the whole other part of the box. Then we have a velocity 1 final, which we know is 20 meters per second, and the velocity of the second piece is what we want to find. Okay? So one more thing we need to be careful of is this momentum is a vector, so we do care about the direction of this box. So we can denote this right motion as positive, and so the opposite direction will be negative. So the initial velocity is going to be in the positive direction, and we know since the second piece is coming off in the positive direction, it's also going to be in the positive direction. So both of these velocities will be positive. And then if we get a final answer that's negative, we just know it's moving in the opposite direction. And if it's positive, it's moving in this rightward direction, or the same direction as the initial block. Okay, so now we have to find the velocity of the other piece. So we know we can use conservation of momentum since it's a constant velocity, no net force. So P initial equals P final. And so we can now get all our pieces of momentum. So the initial one is just M naught V naught equals the M1 final, V1 final, plus M2 final, V2 final. And so now we have all these variables except for V2 final. So we can go ahead and rearrange this equation. But first, actually, we can actually plug in what we have here. Since we're not, for the masses, we can go ahead and plug them in. And so our M naught we know is just M, and V naught, I won't plug in the numbers yet. M1 final is 1/4 M, V1 final, and M2 final we know is just 3/4 M, V2 final. And so now the reason I did that is because these masses are going to cancel, because they're all relative to the same mass. And so we can now just get this in terms of velocities. And now we can rearrange it for V2 final. And you could rearrange it first and then plug everything in, the masses would divide out, but this just simplifies the equation a little bit. So now we can rearrange it. 3/4 V2 final equals V naught minus 1/4 V1 final. And if we go ahead and plug the rest of these in, or rearrange the fraction, we'll get 4/3 V naught minus 1/3 V1 final. Okay, and now we have all these values, so we can go ahead and solve for this and say V2 final equals 4/3 V naught, which is 15, minus 1/3 V final, which is 20. And so this gives us a value of 13.3 meters per second. And so now we know the other piece will be moving at this velocity, and since it's positive, it'll also be moving in the same direction as the initial block. So if we think about this, the block is moving forward, it breaks, and now these both still move forward, but this one's going to move slower than the original block, and this one's going to move faster. And the reason is because the system's center of mass velocity is not going to change. And so let's talk about what that means right now. So center of mass velocity is just the sum of the momentum divided by the sum of the masses, which we can break up into the mass times velocity and summing those with the total mass. And so we can actually get this just by using conservation of momentum, because we know that if the P naught and P initial equals P final, if we know that the P initial is the sum of the momentums initially, and the final is just, let's say we have like multiple pieces and they come to one blob as moving as a V final. Now we have the total mass times the V center of mass because it's just one velocity, and we can divide by this M, and we get the sum of the momentums over the mass. And so when momentum is conserved, so is the velocity center of mass. And so let's go back to that initial equation here, or this initial problem, and let's solve for the velocity center mass using our our final velocities and see why this matters. So we know that the velocity center of mass initially, let's do this in a different color. We know the velocity center of mass initially, there's only one piece initially. There's only this initial block. So it's going to be 15 meters per second because it's just the velocity of that block. And then, so that's initial. But now our final velocity, we have to use our equation. So our final center of mass velocity, since we have multiple pieces, we have to do the sum of the mass times velocities over the mass. And we could still do the sum of the mass times velocities over the mass, but since there's only one piece, the masses are going to cancel and we just get that center of mass velocity right there. So when there's one piece, you can just pull it straight out, but even if you use that equation, the masses just cancel. But in this case, there's multiple masses multiplied by different velocities, so that's why we have to use this. So we can break this up into each piece. So we have the 1/4 m v1 plus the 3/4 m v2 divided by the total m, which is just going to be m. And so now these masses end up canceling, and we can plug in the values we solved for. And if we did the first question correctly, we should get the same velocity. So this one's 20 plus the 3/4, and this is what we solved for, the 13.33. And this is just over 1 since the masses got canceled. And when you plug this into your calculator, you'll get 15 meters per second, which is the same velocity as initially. So this velocity center of mass did not change. And so that's whenever the momentum is conserved, so is the velocity of the center of mass. And so that center of mass velocity doesn't change when the momentum is conserved. Okay, so that's all I got for this video. Make sure to watch the next one where we go over different types of collisions and how we can use conservation of momentum, and when the energy is conserved during those collisions. Alright, thanks for watching.